Let's quickly review what we have learned in the previous two sessions. We learned how to estimate a population proportion. We always use the Z table, right? The standard normal distribution table to do that. And we learned what is the best point to estimate of the population mean, a population proportion. We learned how to construct the confidence interval, which means we're using the confidence interval to estimate the population proportion, and also we learned what is the sample size that would be needed in case we want to have the confidence interval to be at a certain confidence level. That is everything we know we learned for the population proportion. And in the previous session, we learned how to estimate a population mean, and that in that session we learned a new distribution. It's called a T distribution, which is a very, very good distribution that has the degree of freedom. It's very different than Z. I showed you a little flow chart, like when you're going to use the Z, when you're going to use the T. For the estimating a population mean, we also learned how to do the point estimate, how to do the confidence interval estimate. Of course, it depends on whether you're going to use a T or Z. You're going to have a different critical value. And then you do the different calculation. And then we also learned how to calculate the required sample size if you want to estimate a population mean in order to have the maximum margin error, which is whatever number is given, then you know how to do that. Now, in this session, we're going to do this. We're going to estimating a population standard deviation. A population standard deviation or variance. Okay, again, what is the letter for the population standard deviation? That's a sigma, and the variance will be sigma square. So what do you use? You use the sample standard deviation, which is S, or the sample variance is S squared. So you're going to use this S to estimate a sigma, or use S squared to estimate the population variance. The only difference is, I don't know if you remember that, this is unbiased. And this is a biased, but there's nothing else we can do, right? And that's it. So the sample variance S squared is the best point estimate of the population variance, sigma squared. And the sample standard deviation S is also the best point estimate of the population standard deviation, sigma, even it is a biased estimate. Okay, then we need to get this is for the point estimate. And then we need to get the confidence interval, right? It's the point estimate, confidence interval, sample size. Those are the three things we worried the most. Okay, how do you construct the confidence interval? I'm going to introduce you a brand new distribution. It's called a chi-square. So for the confidence interval for sigma or sigma square, we're going to use chi-square distribution. Okay, this is a Greek letter chi-square. Don't think that's something square. This is a whole piece. Okay, it's just pronounced as a chi-square. It's not like I give you a number, you square it. No, it's just one notation for a single value. A lot of people get confused here. They always want to do square. No, you don't need to. Okay, so how do you find that? How do you find the chi-square distribution? And again, if you Google online, then you're going to find numerous tables for the chi-square distribution. Did you notice here degree of freedom? That's the same thing as our T, right? It has the degree of freedom. And here the critical values for chi-square is also right tail and the significance level alpha. Now, if you might have noticed that here is a 0.99 and all the way here is a 0.01. Let me tell you what the chi-square distribution look like. Okay, the chi-square distribution looks like this. That's weird, isn't it? Because here is a 0. So for chi-square distribution, there's no critical value less than 0. So in other words, there's no negative critical value for chi-square. Therefore, if I'm asking for 95% confidence interval, then I have to put this little tail as 0.025, and this tail, let me shade it. This tail is also 0.025. Then you're going to get two critical values. We call this as right, we call this as a left. So this one is the chi-square right, and this one is the chi-square left. All right, now let me show you how to do that. For example, I give you the degree of freedom equals, let's see, I find the degree of freedom is 10. Let's try that. So by looking at this table, here is the degree of freedom 10. So we're going to use this one, right? And remember, this one is the right tail area. So for here, the right tail area is 0.025. So we just need to look at here. The right tail is 0.025, a degree of freedom 10, so we get a 20.483. So this number is 20.483. That is your one critical value. What about this guy? This number we're looking for. The right tail is, because the whole area under the curve is 1, and this is shaded, this really dark triangle is 0.025. So the right tail should look for, it's 0.975, right? It's 1 minus this guy. So if you look at for 0.975, with the degree of freedom 10, you get a 3.247. All right, so now you know how to find the left and the right critical value. Try one more. Try one more. Again, that's the chi. Okay, the chi-square looks really weird. Okay, so here's a 0, and this is a chi-square, and this degree of freedom so far. Let me make it a 20. Okay. And when the degree of freedom is 20, you might notice it's pretty flat. It's flatter than that one. So when the degree of freedom goes higher and higher, the distribution goes like a flatter and flatter. Now let's look at for same thing. Let's for 95% confidence interval. Okay, so here and here we need a 95% in the middle. So this is 0.025. And here is also 0.025. That's this area here. All right, now if you look at a chi-square distribution for the right tail, 0.025, degree freedom 20, 0.025, degree freedom 20, we get a 34.170. So here's a 34.170. And similarly for this guy, for this point, this chi-square value we're looking for, the right tail should be 1 minus 0.025, so we should look for 0.975. So 0.975 degree freedom 20. Do you see here? 9.591. So here's 9.591. Okay, now if you compare this to, this is the degree freedom 10, this is the degree freedom 20. Do you see that it's shifted to the right and also flatter? Okay, so that's how you'll find the critical value of a chi-square. Now we're going to work on a real example. We're going to work on the example here. All right, now a simple random sample of a 22 pulse rates is obtained. So we have the n equals 22. Okay, and then construct a confidence interval for the population standard deviation sigma. So we need a CI for sigma. That's what we're looking for. Okay, and that will require the left and the right critical value of chi-square, and we want the confidence level to be 95%, So 95% CI, and also the we have the sample size 22. I think that's about it. Okay, so that's we're looking for the critical value. 95%, n is 22. You know what is the degree of freedom? Degree of freedom here is also n minus 1. Let's keep this in mind. So we should look for n minus 120. So the degree of freedom should be 21. So let's find out chi-square left and chi-square right. Okay, 95%. So the right tail is 0.025. Degree freedom is 21. So it's a 30, sorry here, 30, 21, right? So 35.479. That's the right side. So it's a 35.479. And the left side, you should look at 0.975 with a degree freedom 21. So it's a 10.283. So 10.283, right? So this is the third time we practice this and we get that. All right. So we get the critical value now, and I will give you the formula for the confidence interval. Are you ready? For the confidence interval for sigma, that will be between n minus 1 sample variance over chi-square left, because the left number is always smaller, so you divide by smaller number, so this value is greater. So here is n minus 1 and s square over chi-square right square. Okay, so what about a sigma? So that will be the square root of n minus 1 s square over chi-square L, and here will be n minus 1 s square over chi-square right. Okay, now keep in mind what you find here is a chi-square left square, so that's this thing. So the whole thing here is a 10.283, and the whole thing here, the denominator, is a 35.479. So don't take a square again, okay, because this one already have a square. Now in our example, if I give you the data, if I give you the list of numbers, let's see, if I give you the S is 9.91959, okay, can you find the 95% confidence interval estimate of sigma? I need 95% CI for sigma. Yes, because we can just plug that into this formula, and we have n is 22 and the degree freedom is 21. We already have this two critical value, so let's just plug in the number here. So that's going to be 22 minus 1 times 9.91959 square, right, divided by chi-square right. We have that 35.479. Please do not square this number again, because that's the chi-square. Okay, so that will be like this, and then here's 22 minus 1, 9 point, here's multiplication, 9.91959 square. So you have this guy square, okay, and then divided by, here should be the chi-square left. We have a 10.283, so 10.283. Now I ask you to stop the video and then to figure out the answer for both. Okay. All right. Now you have this between. This is a 14.2 and this is a 7.6. All right, for all those 22 numbers, they're the pulse rate. And the pulse rate has, we try to estimate the population standard deviation, and we found that is 7.6 BPM, beats per minute, and then this is BPM. So that's your confidence interval, 7.6 to 14.2. Okay, so that's your that's your confidence interval, 95% confidence interval for sigma is this. All right. Now, do you remember our S is 9.9 something? But this one, did you notice that it's not from 9.91959? Just add or subtract the maximum error or the margin of error. We don't do it that way. So this is very different because T and Z, these two distribution, they're symmetric along this the y-axis, but not chi-square. So chi-square, you don't use that. That's why we don't need to worry about the margin of error in chi-square at this moment. Okay, so you have the confidence interval. If you add this two number divided by 2, you get a 21.8. So the average of that if you use that divided by 2, you get a 10.9, which is very different than this. So this one, the sample standard deviation, is not right in the middle of your confidence interval. Okay, and if you cannot just given by, if you're given the confidence interval, you cannot use this, add them up, divide by 2 to get the sample standard deviation. Of course, you're not going to get the E. Now, you might ask this question, wait a second, if that's the case, how do I find the sample size? That's a very good question because it's hard. It's hard to find the sample mean. So I give you two tables. Okay. The first table, let me just make it really big. I will write this for you because I think this is kind of important. One is you want to be 95% confident that S is within 1% of the value of sigma, the sample size should be at least 19,205. I just give you this number. So I give you this little table. If you want to be 95% confident that your S is within 1% of 1% of the values of sigma, the sample size should be this much. If you want to be 5%, if you want to be 95, there's so many percentage here. You want to be 95% confident that S is within 5%. We just talk about the relative, right? The relative error. So 5% of the value of sigma, the sample size should be 768. And if it's 10%, you get 192. If it's 20%, then you get a 48. If it's 30%, then it's 21. Okay, 40%, 12, and 50%, 8. So that's one table. If you want to be 95% confident that your S within this much of the value of sigma, then here's the sample size. Can you see that? If you want the S is within the larger percentage of the error, which is the error of the value sigma, then the smaller sample size you would need. If you want to be super precise or very precise, then you need a huge sample size. So this is the table if you want to be 95% confident. And there's another one for 99. So for 99, I probably want to use the red color. And of course, you will give 99%. Okay. And you'll be given this two table if during your quiz. Okay, so if you want to be 99% that S is it's within 1%, 5%, same thing, 10%, 20, 30, 40, and 50%. Let's see what's your sample size. Here should be 33218. This one should be 1336336. Then 85, 38, 22, and 14. Now, keep in mind when we want to estimate the variance or the standard deviation, we are not using the formula. We just use this table to find the sample size. Okay, so please don't try to go back to some formula, just use this table. And the other thing I want you to know is if you want the error, the margin of error to be greater, then you only need a smaller sample size. If you want to increase your confidence level from 95 to 99, you want to be more confident, then the larger sample size you would need. Okay, so you just get this rough idea. And then next, I think that's the last one. We're going to do just one quick example here. Okay, basically just show you how to use this table. We want to estimate the standard deviation sigma. Okay, and here, hold on. Of all pulse rates of adult women, we want to be 99% confidence. That's your confidence level. You want to be 99% confident that our estimate is within 5% of the true value of sigma. How large the sample size should be. 99%, we're going to use the red number, right? And then we want to be 95%. So the answer is 1336. There you go. I think that would be the easiest answer, isn't it? Yeah? Okay, so we should obtain a simple random sample of 1,336 pulse rates of adult women. Period. That's your answer. All right, so in this session, we learned chi-square, which is a very interesting distribution, and we learned how to use that to find the critical value, to construct the confidence interval for the population, standard deviation, and the variance. All right, so far we learned almost everything about this interval estimate from the sample. Okay, so the whole chapter we're going to have a quiz.